Hello friends, today we shall start with the module number 4, the field effect transistor. The field effect transistor, in short, it is called as FET. So the FET comes in several forms, that is in a junction FET. In short, it is called as JFET. In JFET, the control or the gate, there are three terminals here: drain, gate and source. So the gate, which acts as a control here, the control voltage varies the depletion width of a reverse biased PN junction. Similar to the JFET, there is one more device in which the junction is replaced by a Schottky barrier. That is, it is called as metal semiconductor FET. In short, MES FET. Again, there is an alternative to this. The metal gate electrode may be separated from the semiconductor by an insulator. So it is metal insulator semiconductor FET. It is called as MIS FET. Then one more, a common special case of this type uses an oxide layer as an insulator. So that is metal oxide semiconductor field effect transistor, MOS FET. So these are the various forms of the FETs. So first let us discuss basic PN junction operation. The figure shows the cross section of a symmetrical N channel PN junction FET. So the junction field effect transistor, along with some other circuit elements, it is capable of voltage gain and signal power gain. The current in a JFET is through a semiconductor region which is known as the channel. So in between the N region that we can see in the figure is known as the channel. So based on the channel, it is classified as N channel JFET or P channel JFET. So the channel with ohmic contacts at each end are available. The basic transistor action is the modulation of the channel conductance by an electric field that is perpendicular to the channel. So in a JFET, the voltage variable depletion region width of a junction is used to control the effective cross-sectional area of conducting channel. So the N region between the two P regions is known as the channel. So you can observe there are two P regions. The P regions are connected with a gate, and in between there is a N region. So that N region is a channel, and in this channel the device, and in this N channel device, the majority carriers are electrons because it is N channel. So the majority charge carriers are electrons which are going to flow between the source and the drain terminals. Observe the source and the drain terminals. So the majority charge carriers are going to flow between the source and the drain terminals. The source is the terminal from which the carriers enter the channel from the external circuit. So the source, as the name suggests, the source is the one of the terminal of the JFET, from which the carriers are going to enter into the channel from the external circuit. The drain is the terminal where carriers live or drained from the device, and the gate is the control terminal. So the end of the channel from which electron flow is called the source, and the end towards which the flow is called the drain. The P plus regions are called the gates. So if the channel were P type, so this is a N type channel, and if it is a P channel, then holes would have flow from the source to drain in the same direction as the current flow, and the gate regions would be N plus. The two gate terminals shown in this figure are tied together. You can observe both the gates are connected. So they are tied together to form a single gate connection. So actually JFET has 4 terminals, out of which 2 terminals are tied together. They are gate terminals. So they are going to be tied to form a single gate connection. Since majority carriers, that is electrons, are primarily involved in the conduction in this N channel transistor, the JFET is a majority carrier device, or it is called as an unipolar device. So as we have discussed, a complementary P channel JFET can also be fabricated, in which P and N regions are reversed from those of the N channel device. That is, the holes will flow in the P type channel, because in P type channel holes are the majority charge carriers, and they are going to flow between the source and the drain, and the source terminal will be now source of the holes instead of electrons, like in N channel device, and the current direction and voltage polarities in the same direction. A P channel JFET are reverse of those in the N channel device. So the P channel JFET is generally a lower frequency device than the N channel JFET due to the lower hole mobility. So it is common practice to connect the two gate regions electrically. Therefore, the voltage VGS refers to the potential from each gate region to the source S. Since the conductivity of the heavily doped P plus region is high, we can assume that the potential is uniform throughout each gate. In the lightly doped channel material, the potential varies with position. If the channel of this figure is considered as a distributed resistor carrying a current ID, so that ID is the drain current. So current ID, it is clear that the voltage from the drain end of the channel D to the source electrode S must be greater than the voltage from a point near the source end to the S, that is source. For low values of current, we can assume a linear variation of voltage. in the channel varying from Vd at the drain end to 0 at the source end. Now let us discuss the N channel JFET under different gate bias. The first one is a zero gate bias. So gate bias is not applied. So it's a zero gate bias. So the figure shows the gate to channel space charge regions and IV characteristics for small VDS values and for a zero gate voltage. So both the figures are shown here, gate to channel space charge regions and a IV characteristics for VDS versus ID. So as shown in figure, if a negative voltage is applied to the gate of the N channel JFET, if source is at the ground potential, source is grounded here, and if a small positive drain voltage is applied, that is plus VDS, source is grounded and a small positive drain voltage is applied to the drain terminal, that is plus VDS, a drain current ID is produced between the source and the drain terminals. So the N channel is essentially a resistance. So the ID versus VDS characteristics for small VDS. If you vary a value of VDS very slightly for a small VDS value, it is approximately a linear. So as you can see from the figure, the characteristics between the VDS and ID are linear characteristics when VGS equal to 0. The gate to source voltage is 0 and you are applying a small positive voltage at the drain terminal, you will get a linear characteristics. So this is when the zero gate bias voltage, that is VGS equal to 0, and you are applying a small positive voltage across the drain terminal and the source terminal is grounded. For a small value of VDS, you will get a linear characteristics as shown in the IV characteristics diagram. Second one, small negative gate voltage. So similar to the previous one, so source is again grounded here and the drain is with a small positive voltage, whereas for the gate VGS, if you apply a small negative gate voltage, what happens? So here the figure shows the small reverse biased gate voltage, because as you are applying a negative voltage to the gate terminal, it is a reverse biased gate voltage. If a negative voltage is applied to the gate of the N channel PNJFET, the gate to the channel PN junction becomes reverse biased. So as the gate is positive and you are applying a negative voltage, it becomes a reverse biased. So the space charge region now widens. So observe the blue color shaded mark in the diagram, so which is nothing but the space charge region. So in the previous figure it was very narrow, now in this figure it is little bit widens. So the space charge region now widens, it becomes little bit large, so the channel region becomes narrow. So the N channel becomes little bit narrow than the previous case. N channel becomes narrower and the resistance of the N channel increases. As the channel becomes narrow, the current flow through that one will observe a resistance. That's why resistance of the N channel increases. So observe the characteristics diagram, the slope of the ID versus VDS curve for a small VDS decreases. So for the VGS equal to 0, we have a linear characteristics, whereas here the slope of the ID versus VDS curve for small VDS, if you apply a negative gate voltage, then it is decreases, slope is going to decrease, that is indicated by VGS equal to minus V1. So minus V1 is a small negative voltage. As you are applying a small negative voltage, the slope is going to decrease compared to the when gate voltage is 0. Now the third case, when you apply a large negative gate voltage. So here the figure shows when you apply a gate voltage to achieve a pinch off. So here we consider the channel in a simplified way by neglecting voltage drops between the source and the drain electrodes and the respective ends of the channel. For example, we assume that the potential at the drain end of the channel is the same as the potential at the electrode D. This is a good approximation if the source and the drain regions are relatively large, so that there is a little resistance between the end of the channel and the electrode. If a large negative gate voltage is applied, the condition that is shown in the figure will be achieved here. So you can observe the variation between the first case, second case and the third case. So you can observe the blue color shaded mark in the circuit is completely touched from the above P plus and below P plus. So there is no, in the channel there is no space. So that is the difference when a large negative gate voltage is applied. So if a large negative gate voltage is applied, the condition that is shown in the figure will be the result. The reverse biased gate to channel space charge region has completely filled the channel region. So because of the large negative gate voltage, that is VGS equal to minus V2. Other two conditions are same here, that is source is grounded and a small drain voltage VDS is applied. But if you apply a large negative gate voltage, that is VGS is minus V2, that is whatever the previously you have applied a small negative voltage, gate voltage, so greater than that negative voltage is applied. If you apply, so what happens, the reverse bias gate to the channel space charge region has completely filled the channel region. The space charge region is completely filled the channel. So this condition is known as pinch off. So the drain current at pinch off is essentially 0 here, as the space charge region is completely occupied the channel. So there is no space for current ID to flow between source and gate. So the drain current at pinch off is essentially 0, since the depletion region isolates the source and the drain terminals. So since the resistance of this channel is higher, so resistance is very high here, the IV plot for the channel begins to depart from the straight line that was valid at low current levels, as the voltage VDS and the current ID are increased still further, the channel region near the drain becomes more constricted by the depletion regions and the channel resistance continues to increase. So as VDS increased, there must be some bias voltage at the depletion regions meet near the drain and essentially pinch off the channel. So when this happens, the current ID cannot increase significantly with further increase in VDS. So beyond pinch off, the current is saturated approximately at its value at pinch off. So you can observe the characteristics, IV characteristics. For VDS and ID values, if you apply a negative gate voltage, a large negative gate voltage, VGS equal to minus V2, as there is a pinch off, that is space charge region has already occupied the channel, there is no space for current to flow from between the source and the drain, the current ID is essentially 0. That's why VGS equal to minus V2, the slope is almost equal to 0. That is shown in the IV characteristics. Now the next, N channel JFET under different drain voltages. Previously we have changed the gate voltages. Now we will change the drain voltage VDS and we'll see the characteristics curve. Now the first case, a small drain voltage. Now this figure, the small that is figure shows a small drain voltage. This figure is exactly similar to the first case that we have discussed in the N channel JFET under different gate bias, that is 0 gate bias. So both are same here because the source is grounded and we are applying a small positive voltage VDS and VGS is 0. So that case we have considered as 0 gate bias. Here we are considering this case as a small drain voltage. So both are same here. So now consider the situation in which the gate voltage is held at 0 volts, VGS equal to 0, and the drain voltage changes. So here in this case, the N channel JFET under different drain voltages, we are varying the drain voltage. In previous case we have kept the drain voltage constant with some positive voltage. Here we are varying the drain voltage by keeping the VGS equal to 0. So this figure is a replica of a figure in 0 gate bias. So for 0 gate voltage and a small drain voltage, so the characteristic curve is also shown here, VDS versus ID. Now this is a second figure, second case, a large drain voltage. So figure shows a large drain voltage. So as you can observe here, again the source is grounded and the VGS is held at 0 volts, but the VDS, drain to source, VDS, that at the terminal, drain terminal, the voltage is increased, VDS is increased, the plus sign, in previously it was plus sign, here plus sign means there is an increase in the VDS. So as the VDS or the drain voltage increases towards the positive side, the gate to the channel PN junction, so observe, gate to the channel PN junction becomes reverse biased near the drain terminal. So observe the space charge region, it is becoming wider at the drain terminal, whereas it remains the same at the to near the source terminal. So it becomes reverse bias near the drain terminal, so that the space charge region extends further into the channel. So it becomes, the space charge region is getting widened and extends further into the channel. Here the channel is essentially a resistor, and the effective channel resistance increases as the space charge region widens. So as there is a increase in the channel, as the channel widens, the resistance increases because there is less space to flow the current. Therefore, the slope of the ID versus VDS characteristics decreases as shown in the figure. You can observe for the low VDS, earlier the current ID was increasing linearly, but as VDS increases further, the channel, it changes the channel resistance. So the slope getting bend. The effective channel resistance now varies along the channel length, and since the channel current must be constant, the voltage drop through the channel becomes dependent on position. So this is what when the drain voltage is increased. Now we'll see the third case, a drain voltage to achieve pinch off. So we have already discussed what is pinch off, but in this case, after increasing more and more drain voltage towards the positive side, what happens? So this figure shows a drain voltage to achieve a pinch off at the drain terminal. So whatever the condition that is shown in this figure, you can observe the space charge region, that is it is marked with a blue color at the drain end. So it is again extended, widened, and they touched each other. That means there is no space to flow current between the source and the drain. So this happens when you increase the drain voltage VDS, that is you can see plus VDS, that means a higher positive voltage at the drain terminal to achieve the pinch off. So a condition as shown in this figure is achieved if the drain voltage is increased further. So the channel has been pinched off at the drain terminal. So if any further increase in the drain voltage will not cause an increase in the drain current. So as you can observe the characteristics curve here, at some particular point of time, that is VDS, ID has increased sufficiently, and even if you increase further VDS, ID, that is drain current, remains the same, it remains the constant, so which is called as saturation region. It is marked with a saturation region, that is more and more positive voltage, drain voltage, if you increase, there is no change in the drain current remains the same and it go into the saturation region. So this is called as pinch off. So any further increase in the drain voltage will not cause an increase in the drain current. So the IV characteristics for this condition is shown in the figure. So the drain voltage at pinch off is referred to the VDS SAT. So drain voltage here in this case is called as VDS SAT. So for the condition VDS is greater than VDS SAT, that is VDS is greater than saturation voltage VDS, the transistor is said to be in the saturation region, and the drain current for the ideal case is independent of VDS. So this is about a drain voltage to achieve the pinch off. Then finally, a expanded view of the space charge region in the channel for VDS is greater than VDS sat is shown here. So the figure shows an expanded view of the pinch off region in the channel. So observe here carefully, the N channel and the drain terminals are now separated by a space charge region which has a length delta L. So observe the delta L. Delta L is the change in the length. So the N channel and the drain terminal. Observe N channel and the drain terminal are separated by a space charge region. The blue color shade is nothing but a space charge region. It is marked with a delta L, that is, it's a change in length. So the electron move through the N channel from the source and are injected into the space charge region where it is subjected to the electric field force. Electric field is also shown. They are swept through into the drain contact area. So if you assume that delta L is much less than L, so the actual length L is shown here. So delta L is much less than L, then the electric field in the N channel region remains unchanged from VDS SAT case. Once the carriers are in the drain region, the drain current will be independent of VDS. So this is about expanded view of the space charge region in the channel for VDS greater than VDS SAT. Thank you for watching the video.